Now let's see if we can actually use our model to make a quantitative prediction to see if we can get something close to this. So this is a Python program that we're actually going to use to see if we can predict the speed of sound in two different metals based on our values for the interatomic spring stiffness, which we get from stretching wires and getting Young's modulus, and the mass of the atoms, the distance, the length of the bonds. So here's the basic idea. We're going to model a wire or the rod as a chain of atoms, chain of these balls connected by springs, and we're going to tell the computer that the mass of one of these balls is the mass of the atom of interest. We're going to start with aluminum, and the spring stiffness is the stiffness of the interatomic bond. And for aluminum, I think that comes out to something like 16 newtons per meter if we do that calculation. And so what we're going to do is going to bang on one end of our model, and so we're going to give that an atom at that end a bang to the right, just like we did. And the springs are invisible here, so all you're seeing are the balls moving, but that's going to compress the next spring, and the next ball is going to start to move, and this is going to travel down the chain. And that's a little hard to see, so we're going to make a graph. We're going to graph here the displacement of each atom from its equilibrium position. So what this looks like is this atom has now moved in the plus x direction from its equilibrium position. And now at this time, so we're going to step through it. And now this atom's moving and that atom's moving. And how's the computer doing the calculations? It's actually doing it step by step, just the way we outlined here. For a given atom, it looks at the spring to the left and sees if it's compressed or stretched and what the direction of the force it's going to exert is. And then it looks at the spring to the right, and it sees if that's compressed or stretched and what that force is going to be. Calculates the net force. Says P final is P initial plus F net delta T. Changes the momentum of the atom. Takes a time step and does it again. It does it for every atom over and over again. So we get this pulse, this wave propagating toward the end, and then it stops. Okay, now we want to do it for a lot of atoms. So down here at the bottom, we've got 100 aluminum atoms, and the diameter of aluminum atoms, so the length of a bond, is 2.6 times 10 to the 8th meters. They're pretty big. And so what we're going to do is tell the computer to start. We're going to just give an impulse to this atom. It's going to do all these calculations, calculating the force on each atom and the new momentum and updating momentum and doing it again and again. And we're just going to click to stop it when it gets to the end. So, and we're going to watch the graph. So here we go. I think. There we go. And so I stopped it. And in virtual computer time, taking little tiny delta t steps, we ran for 4.9 times 10 to the minus 12 seconds before it got to the end. And I may have stopped it a little soon, so maybe we're estimating a little bit faster. The total distance, all these atoms together, was 2.5 times 10 to the 8 meters. And so we divide and we find that the speed that we predict is about 5,000 meters per second. Now, a typical measurement of the speed of sound in aluminum, a more accurate measurement than we did, is around 4,800 meters per second. So that's not a bad prediction, actually. Our models, we're in the right ballpark. To confirm this, let's do it for a completely different substance. Let's try lead. Lead is, I think, as you know, it's not great to touch it because it's toxic, but it's a very soft material. Lead atoms are very massive. The interatomic springs are very soft, about 5 newtons per meter. And so if we take, so the atoms are bigger, so if we take in our computer model 82 lead atoms, each with the mass of a lead atom and a spring stiffness of 5 newtons per meter. And we do the same thing. We just let the computer run, applying the momentum principle to every atom in the chain over and over and over and over again, iterating and iterating and iterating. We can see that this is taking a lot longer. And this time I'll be a little, okay. So it went 2.5 times 10 to the negative 8 meters in 2 times 10 to the minus 11 seconds. So the speed predicted was about 1,200 meters per second, which is indeed the speed that gets measured for the speed of sound in lead. So by using exactly the same model, this model, but just using a different atomic mass and a different spring stiffness, which we got from Young's modulus, we're actually able to do pretty good predictions of the speed of sound in solids, and that's encouraging because it says that our model is certainly capturing some of the essential factors that determine the behavior of this material. And notice that we started out hanging weights on wires, not banging on the ends of things. So a very different set of measurements went into making this prediction work. So this is encouraging. And in fact, notice how simple our model was. It was just one chain of atoms. Okay, so we said, well, we'll just consider one chain that got hammered on. So of course we're saying that these atoms that are connected by transverse springs move together, and there's not much action there. You know, even so, it was we're doing quite well. We're doing much better than a factor of 2, and we're really getting the right order of magnitude. So this is evidence that the kind of microscopic model we've been making is useful and valuable, and really does tell us something important about what's going on inside.